Here we're going to talk about work, energy and power. Work and energy has a symbol W. You can see other letters as well, but here we use W. The unit for work and energy is joule, and we can see it can also be kilojoule and megajoule, but just to give a reasonable number. So work and energy has the same unit, and we also know if we have to do some work, we have to get in some energy. So that can both be for people and machine. So if a machine has to do a work, it has we have to give the machine some energy. It can be electrical energy, it can be fuel for an engine or whatever. We also got power. It's the capital letter P for power, and the unit is watt. Here we also can see we can have kilowatt and megawatt and so on, just to give a reasonable number. And the relationship between power and work, energy, is that if we have to do some work, we perform with the power in a given time. So if we have to do the work in a short time, the power must be high. From physics, we also know that work is the force times the distance. So here we got two equations where we got the same value over here. So these two, power times time and force times distance, must be equal to each other. We can say that just to find out what we can create with these two formulas. And if we just then take the power divided by the force, we have the distance divided by time, and distance divided by time is the velocity. So it seems to be that the power divided by force is velocity. We can make a control by the unit because we know that velocity is measured in meter per second in the SI system. Power was watt and force is Newton. The power, here we got the symbol for the unit, watt. The W over here is not the symbol for the unit, but the symbol for work or energy. So here we got the symbol and here we got the unit. So we have to know that it's very important for the W if it's the unit or the symbol. So W here, symbol is connected to unit is connected to the symbol P for power, and the power is equal to the work divided by time, and work was joule and time is second. So instead of watt we can set joule per second. So now we got some new units, joule per second times Newton. We know from physics that joule is equal to Newton times meter. So we got Newton meter divided by second times Newton. And we can see that we only got meter per second back, and it seems to be correct that power divided by force is equal to velocity. That was just the basic of work, energy, the symbol and the unit, and power, the symbol and unit. For power we also have that we can have 1 horsepower. Here it's not actually a horsepower but Danish hestekræfter, and it means it is a Danish horsepower or metric horsepower, and it is equal to 736 watt. The basic of 1 Danish horsepower is that we have to lift 75 kilogram 1 meter in 1 second. And then we know the power we have to give to this load, so this will happen. We know that power is work divided by time, and work is the force times the distance. The force is the mass of the weight times gravity, and the distance and divided by time. And if we got that the distance was 1 meter and the time was 1 second, we only actually got mass times gravity, and it gives 736 watts. We also can have a horsepower. It's a mechanical or imperial horsepower, and it is 746 watts. There are many definitions of a horsepower in the history, but basically we use this one. It's based on that a horse can turn a mill 144 times in 1 hour, or 2.4 times in a minute. The reel of the mill was 12 feet, so in 1 minute the distance is 2.54, that was the revolution per minute, 2 pi times the diameter, and we got 181 feet. The force of the load is 180 pound force, and it gives the power of, and we know again the power is the work divided by time, or the force times the distance divided by time, and the force one was 180 pound force, and the distance was 181 feet, so it gives 32,572 feet-pounds force per minute. And we say it's nearby 33,000 feet-pound force per minute, and thereby we have the unit for horsepower. In electrical engineering, we know that power is equal to the voltage times the current. Or yes, now we know. And we also have the Ohm's law, that the voltage is equal to the resistance times the current. We can combine these two formulas and get new formulas. So actually over here, for example, the power is equal to the voltage times the current. That could be the voltage for a power supply and the current from the power supply. Then we know how much power the power supply gives to the circuit. And we also know, for example, the power for this resistor is the voltage across the resistor times the current which go through the resistor. Down here we see that still the power is equal to the voltage times the current, and instead of writing the current, we can say that the current must be the voltage divided by the resistance. So we have that the power is the voltage time, instead of the current, voltage divided by the resistor. It gives us voltage across the resistor squared divided by the resistor. So if we have the voltage across this resistor, we can calculate the power by taking the voltage squared divided by the resistance. Maybe it's only the current which is going through the resistor that we know, so we can use the last one. It says that the power is still the voltage times the current, but instead of the voltage we can say, due to Ohm's law, that the voltage is the resistance times current. So here we got the voltage, and we have to multiply by the current, so it gives us that the current squared times the resistance is equal to the power. And again, it is the current which go to the resistor we have to square, and then the value for the resistor.